Okay, anyway, I want to put this just for a second in perspective. So this is the follow-on video from periodic table part 3, actually, in the chapter 7, chapter 8 quantum mechanics chapters. I want to put this kind of in perspective again, is that this, this notion, essentially being able to look at the periodic table and take the theory about orbitals, and again, the extension of the theory that says that an orbital can contain only 2 electrons, a maximum of 2 electrons, all of a sudden then allowed that theory to take shape in the form of the periodic table, which again was already kind of known. The shape of the actual shape of the periodic table was in flux up until this point, but now, given this theory about how the orbitals are arranged in terms of energy, immediately shed some light upon the periodic nature of elements found in nature, and that's why we call it the periodic table. Is that it follows a certain order, and in fact, the way I drew this was kind of intentionally wrong. Is that for the first element, or for the first row, I should say, as we saw with n equals 1, there's only one orbital for n equals 1. That's for when L equals 0 and m equals 0. And so there's only 2 electrons. That happens to be hydrogen and helium. So it's typically drawn like this. But for the next row, we know there's going to be 8 total. And it turns out it's handy, and you'll see that whenever the next row starts, when it's essentially after a noble gas, once you fill a noble gas, which is always filled when the p orbitals are filled, the very next row, and again it's the p orbitals for the same at the same n value as the s orbitals. It's convenient to put the s filling elements to the left, and then have a big blank space here, and then continue on with the p orbitals. 1, 2, 3, 4, 5, 6. Did I miss one? Yeah, sorry. No, that's right. Yeah, sorry. The 6 p orbital ones go to the right. So there's this big gap here because it shows, well, we have the s orbitals being filled, then we have the p orbitals being filled, and then by the time we get to neon, that whole s and p level are filled. Okay. Then when we get down to the third row, we again start with our 3 s ones, which is sodium and magnesium. And then we have a big gap again until we get to the p's. And you remember it's because the 3 level will have the 3s and the 3p, but not the 3d, because 3d is actually higher in energy than even the 4s. So we're going to see the d entries until n becomes 4. That's why when we get to the third period, we still have 1, 2, 3, 4, 5, 6, 7, 8 in that period. The s filling and the p filling at the 3 level. So if you remember when we did this, we had filled all the way up to 3p by the time we got to argon. Okay. Now finally we get to the 4th level, and that's where it gets interesting, because that's where we finally see the first d level orbital. Okay. So here we have potassium and calcium that fill our 4s orbital. That's next. But then instead of a gap here, we actually have a bunch of elements that occur in essentially the filling of the 3D. This is I think this is probably where the early scientists that discovered this one had this big aha moment, because just for a moment, I'm not going to, well, I'll fill in some of these. It was SC, titanium, and it ended with zinc. Okay, there were 10 of them in between there. And again, it must have been remarkable to actually see that it was 10, which happened to match up exactly with with 2 times the number of orbitals at the 3D level. This all from theory. So this all works there. And then finally we get into our 4p elements. I might as well put them in here. With gallium, germanium. What's after that? Arsenic, selenium, bromine. Okay. Shoot, did I botch that? No, I didn't. Okay. So again, these last 6 are the 4 P's. Okay, and these 10 in between were the 3 D's. Now, was really, this is the aha moment, is well, this explains finally why chlorine and bromine and fluorine are all very similar chemically, and for that matter, it explains why lithium, sodium, and potassium are all similar chemically, as are the beryllium and magnesium and calcium. And so now this shape starts to make some sense, especially since once you can rationalize the fact that these 10 don't show up until the 4th row. And similarly, the 14 of the F's don't show up until row 6 for a very similar reason. The 4F orbital doesn't show up until the 6th row of the periodic table. And that's because 4F happens to be higher in energy than 6S. Okay? So anyway, there it is. That's why the periodic table has this shape, and it basically matches up with the orbital theory as well. Okay, I think I'm going to end this one now, since I had kind of 3 videos about the periodic table. I think rather than add another concept in, I'll end this video now and start the next one. Is there anything else I want to say about this periodic chart? Well, I guess not much. There's only, I guess, maybe one thing I want to say is this. If you can think about it, this little 10-element insert, we could have actually kind of left that out and just kind of, shoved in an insert like you see in the real periodic table. You see that we do this for the 14. We actually don't do it for the 10, but we easily could have. We could have said, well, the 10 insert here. And then later we could say, oh, well, and the 14 insert here. It's basically kind of an inserting kind of game. So I just kind of want to mention that. And that's why when we get to the what they call them the inner transition elements, basically the 4F and the 5F that show up after 6S and 7S, they're basically 14 elements that we could have easily truly put in line here, but then this line would have been really, really long. It would have been 2, then 14, then 10, then 6. So it would have been super long. So the periodic table intentionally, we try to make it a little bit more manageable. That's why those 14 are kind of carved out, but they really are meant to be kind of in line. Okay, I think that's probably all I want to say about that.